Hi, Luke McKinney here, Prep 101's Physics 101 instructor. This video is about relative motion, both the mathematical version, finding the relative velocity between two differently moving objects, or the vector version, drawing the triangle and working out the course of a boat or a plane that's being blown off course, or trying to compensate for that.
We're looking at two types of relative motion question today. The first is mathematical, and we can just specify it right at the start. The velocity of A relative to B, which we can write shorter, the velocity of A relative to B, is the velocity of A minus the velocity of B. And likewise for acceleration, the acceleration of A relative to B is just the acceleration of A minus the acceleration of B. Now, what does any of that mean, though? Well, let's have a look. Let's say we have car A speeding along at 20 meters per second. And I'm just standing here, zero velocity. So the velocity of A relative to me is the velocity of A minus the velocity of me. 20 minus 0 is 20 meters per second. So it's getting away pretty fast. But let's say now there's another car chasing it, B. And B is moving at 15 meters per second. So now the velocity of A relative to B is the velocity of A minus the velocity of B, which is 20 minus 15, which is 5 meters per second. So to me, it looks like the car is speeding away at 20 meters per second, but to car B, A's not getting away as fast. From the point of view of B, it looks like A isn't getting as far away as fast. And feel free to put in whichever pop culture chase movie you like best in there. I don't want to date these videos by choosing one because I'll always just choose Mad Max, and that starts to sound a bit silly when you start to say Furiosa and physics in the same thing. They don't really inhabit the same universe. Now, I want to make a little note here for your own equations. You'll notice that these are opposites. The velocity of B relative to A is the velocity of B minus the velocity of A, which is 15 minus 20, which is 5 meters per second, which makes sense. For somebody in car A looking back, it looks like car B is slowly falling backwards. But we notice the effect of this. The velocity of AB is minus the velocity of BA. Now, why do I mention this? Because your own notes present this in a correct but slightly unintuitive way. You'll see in some of your own notes, they say velocity AB is velocity AX plus velocity XB, which is correct in terms of their relative velocities to some third point x, but I find sometimes people have difficulty picturing that. So, because the velocity of AB is equal to minus the velocity of BA, so we have the velocity of AX plus minus the velocity of BX. So it's just the velocity of A relative to some point minus the velocity of B relative to some point. And that's the version I use. I find it just easier to follow and to plug things in. To show an example, let's look at one now. Let's say we have a plane flying north at 400 miles per hour. And we have a jet flying northeast. So that's at 45 degrees at 500 miles per hour. Now we're asked, what is the speed of the plane as seen by the jet? Well, there's two ways to do problems like this mathematically and by drawing a load of vectors and making triangles. I always use the mathematical because it works in every part of the course, for vectors, for force, for momentum, for all of it. So you get more practice out of that method. So let's do it now. Well, how do we do this? Well, what is the speed of the plane as seen as by the jet? That's asking for the relative speed of the plane to the jet. So it's the velocity of the plane minus the velocity of the jet. Now this is a two-dimensional problem. We have x and y. So we break it up. We do x and we do y. So the velocity of the plane in x is 0 mile per hour. It's not going east or west. The velocity of the plane in y is 400 mile per hour because it's going straight north. The velocity of the plane in x is the velocity times the cosine of the angle, which is 353.3 miles per hour. And the vertical component is 500 times sine 45, which is the same answer. So now we do the relative velocity. Like I say, it's in 2D, so we break it up into x and y. The velocity of the plane relative to the jet in x is the velocity of the plane in x minus the velocity of the jet in x, which is 0 minus 353.3, which is minus 353.3 miles per hour, which makes sense. We see the jet is going east. So from the jet's point of view, it looks like the plane is going in the minus direction, west. Likewise, the velocity of the plane relative to the jet in y, the plane y component minus the jet y component, is 400 minus 353.3, which gives us 46.5 miles per hour. Excuse me there, double checking my math. Want to make sure it's all working well. And then, now it always feels good to work out a bunch of numbers, but you always want to check, hang on, did I actually answer the question? We were asked for the speed, which is just the size of the velocity. We've got the x component and the y component. So to work out the speed, it's the square root of the sum of the x squared component plus the y component squared. So we have the square root of minus 353.3 squared plus 46.5 squared, which gives us 356.3 miles per hour. So we've answered the question, but we are practicing today. And remember, whenever you're practicing, don't just think, oh, problem's all done, nothing else to do. You think, well, what else could they ask us to work out? And you realize they could have asked us for the full velocity. What's the angle of this? Well, if we look at it, the x component is minus 353.3. So that's in the minus direction. And the vertical component is 46.5. So if we wanted to find that angle, we could find it from the inverse tan of the y component over the x component which is 46.5 over 353.3, which is 7.5 degrees north of west, which gives us the full velocity of the thing as well. The idea of things catching up with each other or moving apart from each other. The second is with vectors, and this is usually about things being blown or swept off course. A couple of classic examples is, let's say you got a river here. I'll put river there because my art is a little abstract. Now let's say we try to push straight across the river in a boat, but the river has a current with a certain velocity, so it'll be sweeping us down along the river. Now when we add those vectors, we find the result is carrying me off at an angle. Now I'm going faster than I was before. It's a bigger vector, but I'm also going off course. But maybe I don't care about that because this is still the fastest and easiest way to cross the river. The other example is an airplane. Now, if we've got some vehicle with people on it, we want to keep our course. So let's say we've got an airport there we want to go to. we've got a plane here. You can see my amazing art skills, and I want to make sure my result is that I land in an airport, because that is the place we like to land. So we have to account for the wind trying to blow us off course. So what you do is you draw the wind blowing us off course to the airport. Then we aim the plane at the base of that. So then when you add them up, tip to tail like that, the result is where you want to go. So the key in these problems is just which way round you draw the arrows. And then we can use trigonometry to solve the problem. So let's do one of those. Let's say we have a plane that wants to go due north to an airport. So we got our plane, we know we want to go north, and the wind is coming from the east with a speed of 35 kilometers per hour. So we draw the wind coming from the east, 35 kilometers per hour, and then we aim our plane at that. Now we're told our plane has an airspeed of 270 kilometers per hour. That's a term sometimes used in this. The plane compared to the air is going 270 kilometers per hour. Well, what else could it be? Well, now when we add these, we see the result will take us to the airport. And this resultant is sometimes called the ground speed, because that's what it looks like to somebody on the ground just looking up. Hello. Whereas the plane's speed is sometimes called the airspeed, because that's what it's doing in the air. It doesn't care that the air might be blowing it around with the wind and doing all sorts of stuff. So what direction do I have to aim to get to the airport? And what speed am I actually going according to the ground? Well, as soon as you've drawn the triangle, never skip this step. The diagrams always help in every physics problem. We can find this angle now by trigonometry, because we've got the opposite and we've got the hypotenuse. So by SOHCAHTOA, the sine will give it to us. So the inverse sine of the opposite side over the hypotenuse is the inverse sine of 35 over 270, which gives us 7.4 degrees east of north. Don't forget to put down your direction once you just draw an angle. 7.4 degrees, what? East, west, north, or south? You know, always draw and write down what it actually is. Then, if we want to find the actual ground speed, well, that's pretty handy now, because we've got the hypotenuse and we've got the angle. And the ground speed is right next to the angle there, so that's the adjacent. So that's the airspeed times the cosine of the angle, which gives us a ground speed of 268 kilometers per hour. So we can see we're moving a bit slower effectively than the plane's top speed, but we land in an airport because of it. So, you know, that's a worthwhile trade-off.
I hope that was useful. There's plenty more useful videos in the playlist, and even more useful exam-style practice and tips and all sorts of things in the prep sessions. So make sure you join the Prep 101 Facebook Study Hub. You'll find out about everything we're doing there when the prep sessions are on, and there's even sometimes free ones, so you don't want to miss those. Hope I'll see you there.